All right. Good morning, everyone. I hope I'm audible. So, and I think I've already shared the screen. Okay. So, today's goal is to prove Wagner's theorem. And what we discussed yesterday in the second half is that in order to prove Wagner's theorem, it suffices to prove it for three connected graphs, right? And that means that we just need to show the following. Every three connected non-planar graph has a K5 or K33 minor. Okay. Are there any questions regarding why it suffices to prove just for three connected graphs? Right. So that was what we did yesterday in the second half. In fact, we reduced it to simple three connected graphs, but turns out we can prove it for three connected graphs just as easily. So, yeah. Okay. All right. So let me put down the ingredients once more to remind you of the specific statements that we are going to use. Okay, so the first one is our induction tool, which is theorem 9.10 due to Thomason. If you have a three connected graph on at least five vertices, then there exists an edge E such that G contract E is also three connected. Okay, good. Um, Another statement we'll find useful is corollary 10.8, which says the following, that if you have a three connected plane graph and you look at any vertex, its neighbors will lie on a facial cycle after deleting that vertex. So let's say H tilde is a three connected plane graph. Z is any vertex of H. Then the neighbors of Z lie on a facial cycle of H tilde minus Z. Okay. I think I can put a tilde here, it doesn't matter. We are talking about the plane graph. Okay. And finally, we will also find useful theorem 10.25, which is that overlapping bridges are either skew or equivalent three bridges. Skew or equivalent three bridges. And as you can probably imagine, when we have skew bridges, we'll get K33, and when we have equivalent three bridges, we'll get K5. Okay. So these are our main ingredients. All right. Proof. Any questions or concerns regarding these statements that we have proved earlier? So let's begin. G is our non-planar three-connected graph. Okay. And our goal is to show that there is a K5 or K33 minor in this graph. Okay. So let us proceed by induction on the number of edges. right? What that means is whenever we get a smaller non-planar three connected graph, we know that it contains a K5 or K33 minor. Okay,
So here we have to use Thomason theorem, right?
right. That is our induction tool. That's our friend.
So basically, if there will exist an AG for which G contract T will be three connected,
Exactly.
and
Exactly.
since G is non-planar, we can say that G contract T must be non-planar.
No, that we will discuss. That is not true. So
Okay.
let's begin. So by let's me use the numbers by 9.10 Thomason's result, there exists an edge E such that G contract E is three connected. Okay, good. Well, we need to make
So
sure that the
basically,
graph
so
is,
basically, sir,
yeah.
I have a question. So if
Yeah,
G contract T is indeed non-planar, then we are done.
that is exactly the point. Yeah. So if it is non-planar, then we are done. Yeah.
Then we are done. Okay.
So we'll have to look at the planar case. Okay. But before that, we need the graph to have at least five vertices in order to um, use Thomason's result, right? So that is our base case. The base case is when the graph has less than five vertices, four or fewer vertices.
We can't
Okay.
get a non-planar graph, right?
Exactly. Exactly. All of these are planar. Okay. So there is nothing to prove because all these graphs are planar. We only need to prove for non-planar graphs. Okay. Good. Okay. So since we have at least five vertices, we can use Thomason's result. Okay. And we get a smaller three connected graph, smaller by at least one, exactly one edge, right? When you contract an edge, you just lose one edge. Everything else is, yeah, and the number of vertices will go down by one. Okay. So the point is that if this graph G contract E, so let's call this H. Okay. If H is non-planar, then I claim that we are done. There is nothing to prove. Why? Because by the induction hypothesis, H has a K5 or K33 minor. Notice that H is a minor of G. Note that H is a minor of G because we just contracted one edge, so definitely it is a minor of G. And so by the transitivity property that we discussed yesterday, K5 or K33 is a minor of G. Right? So by transitivity, G has a K5 or K33 minus. Okay, so that is easy. If the graph H is non-planar, then we are just done. So we may assume, so now suppose that H is planar. Okay, and let Z denote the contraction vertex. Okay, and let's suppose that the edge E, its ends are X and Y. Okay, so you had a non-planar graph, you contracted one edge, and you got a planar graph. Okay, so what does this look like? Let's draw, consider a planar embedding h tilde of h. Okay. So let's see, what does this look like? Well, maybe let me first put the vertex z. Okay. Now I want to use this result, corollary 10.8. If you have a three connected plane graph and you look at any vertex, its neighbors lie on a cycle. And this is a facial cycle of the graph after deleting that vertex. Okay. So what does the drawing look like? So Z has some neighbors. I don't know, could be as many neighbors. But the point is, after deleting this vertex Z, there is a face that contains all of these neighbors. Right? There could be more vertices on this face. This is basically a cycle. Right? It could look something like this. So here we are using maybe by corollary 10.8, the neighbors of Z lie on a facial cycle, say C, of the graph H tilde minus Z. Okay.
Sir, is the graph G given to be a simple graph?
No, it may
Uh,
not be simple.
Sir,
Yeah.
then if we have a loop in
Hmm.
means on Z, then
Hmm.
Z will be the neighbor of itself. Then how can we use the corollary here?
That is a good point. Okay.
No, but
Um,
sir, I have a
no,
question. So
no, no, no.
how can there be a loop at Z? How can there be a loop
Well,
at Z?
suppose so. What he's saying is, supposing E was a parallel edge like this, right? And you contract E. So now what will happen is you will get a loop at Z.
But sir, I think the way we defined edge contractions, we forbidden the existence of such loops.
No, no. If you have a loop between the edge if you have multiple edges between the if your edge you're contracting is a multiple edge, all the edges that are parallel with that edge will become loops in your new graph. But it doesn't matter. The neighbors of Z do not include Z. So in the case of loops, we'll not worry about it. Also, since you have brought up this point, let me just state at the beginning
Yes, but sir,
that, yeah,
original
go ahead.
graph was simple, right?
Original graph, we did not say it is simple. If you look at the theorem, it doesn't say it is simple,
Okay.
right?
Okay.
But
Okay.
you're right. We will
But we can
actually say
delete edges to make this simple.
exactly. Uh, if you have multiple edges in the original graph, you can just delete them. Planarity is not affected by that, right? So you're done by induction. So another point I would like to make here is we may assume that G is simple. Otherwise, apply induction hypothesis after deleting any edge that is a parallel edge or a loop. Okay, is
Okay.
that fine?
Yes.
So we can assume that the graph is simple. In particular, because the graph is simple, we will not get loops at Z. Okay. Since G is simple, H is loopless. Okay. Good. Any other questions or concerns? All right. So this cycle that you see here is our cycle C. Okay. And it contains all the neighbors of Z. So that's locally, this is what your graph H tilde looks like. Okay. So now what I want to do is I want to go back to the original graph G. Okay. So we have contracted an edge. What is a reverse operation? It is expanding a vertex. Okay. So if you think about going back to the graph G, the cycle that is here will exist as it is. So, okay, maybe I'll just put down the vertices 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10, 11, 12. Okay, that looks correct. So, this cycle is as it is. And what happened at the vertex Z? Well, we had an edge xy, which was the edge E we contracted, right? And when we contracted it, we created the vertex Z. Okay, something like this. We don't know where the neighbors of x and y are. What we do know is that all the neighbors of x and y are on this cycle. Okay, so I won't write that down, that is clear, right?
But sir, I have a question. So here, so the figure on the right, it represents the graph G, right?
Yes, it represents the graph G.
Yeah, but what we have drawn, so is it a so G is a non-planar graph?
Right. So it is not a planar embedding of G. I am just giving you an abstract representation of G, but I want you to relate it to the planar embedding of H tilde, right? So I'm
Okay, okay, okay.
okay.
Okay, sir, okay, sir.
So in
So
particular,
basically
you can take H tilde
in H
and
tilde
you
we
can,
have a
yeah,
contraction vertex Z
exactly,
corresponding to a
exactly,
particular edge. Okay, okay, okay.
exactly, exactly. Okay,
So basically the figure on the left is a planar embedding, but the figure
that's
on the
right.
right is not a planar embedding.
That's right.
Okay, okay.
Exactly. Okay. Good. All right. So now let's think about this. How did it happen that we expanded one vertex Z and we lost planarity? Okay. That's what's going on here. Okay. So I want you to think about for some time about the graph G minus E. Consider the graph G minus E.
But sir, I have a question. So
Yeah.
basically we obtain the graph H from the graph G by contracting the AG.
Yeah.
So if we go in a sort of reverse way, so basically we can say that we are getting the graph G from the
Mhm.
graph H by expanding the vertex Z
Yes.
in some way.
Yeah.
So means so H is a planar graph
Mhm.
because it is a planar embedding H tilde.
Mhm.
And so for a planar graph, we are expanding a vertex Z
Yeah.
and we are getting a non-planar graph.
Yeah.
So my question is when can this happen?
That is what we are going to answer. We are going to find a K5 or K33 here. So the only way this can happen is if you create a K5 or K33, and that is what we want to prove,
Okay.
right? But we will get other kinds of answers to your question on the way, if that is what you are looking for. Okay, we will get answers using bridges, and that will translate to K5 and K33. Okay, all right. So I want you to look at the graph G minus E. There is some disturbance at someone's end.
Also, can you hear me?
Krishnan, your mic, every time you turn it on, there is a lot of disturbance. So maybe you can disconnect and connect again or something like that. It happened earlier too. Oh, yeah, go ahead, Krishnan. I'm reading what you're writing. G is non planar by assumption. You see, we want to show that a non-planar three-connected graph has a K5 or K33 minor. So we started with a non-planar three-connected graph. Does that answer your question? Okay, good. All right, good. Right, so we started with a non-planar three-connected graph. Our goal is to show that there is a K5 or K33 minor in this. We contracted one edge, we got the graph H, and this graph is planar, otherwise we are done by induction hypothesis. Okay, and now we are looking at a planar embedding of H, and we are trying to relate it to the graph G again. Okay, and at the same time, I want you to think of a third graph, G minus E, right? If you think about G minus E, I won't draw it here. You just have to remove this edge, right? So hopefully you can just imagine that without drawing it separately. Okay. So what happens in G minus E? You see, in G minus E, we have the cycle C, and the vertex X, all its neighbors are on this cycle, and the vertex Y, all of its neighbors are also on this cycle. So in particular, X and all its edges and Y and all its edges are bridges of this cycle. Note that X along with all the edges of X, so think of this as a subgraph. It is one vertex and all the edges incident at that vertex. This, and you know what, I'll just write them as sets of edges because we can also think of bridges as sets of edges. Note that partial X and partial of Y are bridges of the cycle C in the graph G minus E. Okay. So what can I say about these bridges? Supposing these bridges, let's call them bridges, let's call this Bx and let's call this By, right? Supposing these two bridges Bx and By, they avoid each other, then what can you say about the graph G?
It's planar.
Exactly. If Bx and V, right, so note that if Bx and By avoid each other, then we can get a planar embedding G tilde of the graph G from H tilde. Okay, let's
So
just,
basically,
yeah,
so basically, then this will be contradiction.
this is a contradiction, exactly, right? So let me just write it down. So if this happens, then we immediately say that this is a contradiction.
So basically, Bx and By they must overlap.
They must overlap. But before we talk about that, let me just make sure that everybody understands this point. Okay, so if these two bridges avoid each other, what does it mean? It means that X has some neighbors. Let's say I gave 3 neighbors to X, and all of the neighbors of Y, they belong to a particular segment. So maybe they belong to this segment. Okay, so then I will put Y here, and I will connect Y to all the neighbors because they're all on this segment, and then I will put an edge between X and Y, right? So that's it, right? It's fairly clear that this gives you a planar embedding of the graph G. Is everybody convinced? Okay, so that's good. So that means that the only way the graph G is not planar if these two bridges overlap. This implies that Bx and By overlap. Well, what does overlap mean? By our previous theorem 10.25, they must either be skew or they must be equivalent three bridges. By 10.25, either bx and by are skew, or they are equivalent three bridges. Okay. Okay, great. So what does that mean? Let's look at the skew case. Supposing they are skew, okay, so which means that I can find two vertices of attachment of x and I can find two vertices of attachment of y so that it looks like this. Do you agree? I must have a vertex of attachment of x, then I must have one of y, then I have one of x, and then I have one of y in that cyclic order on the cycle. And now we put the edge E back in. And what is
Sir, this is a
this?
subdivision of K33, right?
This is a subdivision of K33. The cycle, along with these four edges that I've drawn, joining the vertices of attachment, and the edge E, this gives us a subdivision of K33. Okay? Why is it a subdivision of K33? This is, consider this as a black vertex. These three are white vertices. And this is another, yeah. So you have three black vertices and three white vertices. And there is a path between any black vertex and a white vertex. And these paths are all internally disjoint. So that is exactly a subdivision of K33. Okay? Any questions or concerns?
Oh, sir, I think in this case we should also make sure that none of the attaching vertices are common between x and y.
It doesn't matter. So the point is that they are skew, which means we can find two vertices of attachment for x and two of y, so that these four are distinct and they appear in this order. And I'm just looking at the edges that
Okay,
I've
okay.
drawn and the paths that I've drawn, the cycle,
Okay, yeah.
right?
Sir,
So the
I
cycle
have
along with five edges is a subdivision of K5.
Yeah,
sir, I
yeah,
have a
okay.
question. Sir, I have a
Yeah.
question. So when you are saying two vertices of attachment, you mean at least two?
Well, I want to locate exactly two of x and exactly two of y. They may have 100 vertices of attachment, but the point is that I can find two for x and two for y, so that the four of them are distinct and they appear in this cyclic order,
Okay. Okay, sir.
right?
Okay, sir. Okay, sir. Okay,
So
sir.
there
Okay.
could be more edges here, but I have not drawn all the edges. I'm just drawing enough edges to get the subdivision of K5. Okay. So I'm not going to write down all of this, right? So the cycle C plus five edges give us a subdivision of K33, right? And notice that these five edges, this definitely includes the edge E, right? Because without the edge E, our graph would anyways be perhaps planar, right? Right? So we need the edge E and we need the other four edges joining X and Y to the four attachment vertices that we have found out. Okay, good. So that's that case. So now let's look at the equivalent three bridges case. Are there any questions how we got a subdivision of K33? Is everybody convinced?
So in case of equivalent three bridges, basically both x and y must have exactly three neighbors.
Right. In the case of equivalent three bridges, it is actually more constrained. It means that they actually have exactly three neighbors.
And their set are same.
Right, exactly. So that case is actually much more constrained because in every other case, you can find a subdivision of K33. I'll actually comment a bit more about this in a few minutes. Okay. But you are right. So now let's look at the other case where we have equivalent three bridges. Okay. So let's say X has three vertices of attachment. One of them is this, one of them is this, and there is another here. In this case, there are exactly three vertices of attachment, right? This is a much more constrained case. And then you have Y, and Y also has exactly these three vertices of attachment. And we have the edge joining X and Y. And what is this?
This is subdivision of
Subdivision of
K5.
K5.
Exactly. This is a subdivision of K5. Okay. You have the three vertices that are in boxes here, and you have X and Y. And between any two vertices, you can find a path, and these paths are all internally disjoint.
Sir, we were actually going to prove that it has K5 minor, right?
Right. That is true. You're right. That is a good point as well. So let me just write this down. How many edges are we taking here? 1, 2, 3, 4, 5, 6, 7. Right. So in this
But sir,
case,
I think if a graph has a K5 subdivision, then in automatically has a K5 minor.
that is the key point actually. So we are taking 7 specific edges. Here we are taking 5 specific edges.
No, basically, sir, you gave it in a do-it-yourself exercise at some point earlier that if graph G has a J subdivision, then it is a J minor.
Right. I think the point Kapil is trying to make is we are proving something stronger. Is that what you're saying? Kapil? Can you hear me?
Yes, sir.
Right. So I think so basically in the proof we are finding subdivisions of K5 or K33, right? We are not finding minors. Of course, we know that if the graph is a subdivision, then it also has a minor of the same graph, right? That is an easy exercise.
Sir, we have actually not proved Kuratowski, right? By
We have
this
not
way.
proved Kuratowski. We have not. Because if we were trying to prove Kuratowski's theorem, we
Yeah,
cannot
induction
contract an
hypothesis is
edge.
not correct.
Right, we cannot contract an edge to begin with.
Yeah.
Right? Kuratowski does not allow contraction of edges. That is only allowed in minors. Right? So this implies that G has a K33 minor. This is an easy observation. And this implies that G has a K5 minor. Okay? Good. And that's it. That is the end of our proof. Are there any questions or concerns? How we got a K5 or a K33? So this drawing here is the case of equivalent three bridges. Okay. All right. So in the proof, we are actually finding subdivisions of K5 or K33, but that does not mean we are proving Kuratowski's theorem. The reason is that our first step itself, we are contracting an edge, and contracting edges is allowed in minors, but it's more general than subdivisions.
Sir, why K33 as a K5 is minor?
Sorry, did I write that? Sorry, what's your point?
Why does K33 have oh wait, Wagner's theorem is that
Hmm.
non-planar graph has K5 as a minor, right?
K5 or K33?
Okay. I thought it was only about K5 as a
No,
minor
no,
because
no.
in the
In both
assignment
in
we are
both
using
of
that
them you
only.
need right. In both of them you need K5 as well as K33.
But in the assignment we are supposed to only use that K5 is a minor.
That might be in the assumptions in some problem on the assignment. But as far as Wagner theorem is concerned, you need K5 and K33 both.
Okay.
Okay. All right. Okay, so we are not actually proving Kuratowski's theorem because we cannot contract an edge if we are trying to prove Kuratowski's theorem. That's basically the main point here. We start by contracting an edge, and so we are only finding minors, we are not finding subdivisions. Okay. However, using Wagner's theorem, you can prove Kuratowski's theorem, and that is on your assignment. Okay. So assignment 3 is prove Kuratowski using Wagner. Okay. Another point I want to make here is you see, in the case of skew bridges, you can have lots of vertices of attachment. Whereas in the case of equivalent three bridges, you have exactly three vertices of attachment for x and for y, right? And these are exactly the same set of three vertices. So in that sense, equivalent three bridges is a much more constrained and special case, whereas the case of skew bridges is much more general. Okay, and one of the ways one can sort of dig deeper into that is that actually K33 is more important for non-planarity than K5. And there is a way to explain this. For non-planar three connected graphs, you can actually show that there is always a subdivision of K33. So this is a fact which is beyond the course. I might put it on assignment 4. I'm not sure yet. Maybe I'll just say maybe on assignment 4. Okay. So in the case of non-planar three-connected graphs, there is always a subdivision of K33. All non-planar three-connected graphs have a subdivision of K33. There is one exception. Can anybody tell me what is that exception?
K5 itself.
K5 itself. All non-planar three-connected graphs except for K5, which is non-planar and three-connected, there is always a subdivision of K33. Okay? And that is one way to see why in some sense K33 is the more important one among these two graphs. Okay, and that goes back to why the case of equivalent three bridges is really very specific, whereas the case of skew bridges is much more general. Okay. All right.
But a subdivision of K33 is not three connected, right? Oh, okay. Yeah, it's not necessary. Yeah.
Yeah. Subdivision of K33 won't be three connected unless it is K33 itself. Right? Okay. Good. All right. Are there any questions or concerns regarding Kuratowski's theorem, Wagner's theorem, whatever? Okay. So we started this module by talking about planarity, and I think soon after that we discussed the decision problem, decide whether a given graph is planar or not, right? So we call that DP, decide whether a given graph is planar, right? And immediately we observed that this problem is in the class NP, because to convince someone that a graph is planar, you just show them a planar embedding of the graph, right? And intuitively it is clear that this can be verified in polynomial time. Okay, and then we ask the question, what about co-NP? Can we convince someone easily that a graph is non-planar? Right? So now what is the answer to this question? Can you, yeah, there is disturbance. Yes, okay. Why? Krishnan says yes. Can anybody else explain why this is the case? Why is this decision problem in co-NP?
We can give a no certificate, which is verifiable in polynomial time.
Okay, and what is that certificate?
It's either a K5 or a K33 minor.
Right, exactly. You can either use Wagner's theorem or Kuratowski's theorem. and you can give a certificate.
So
Which
basically,
is
the precisely my certificate is basically a sequence of vertex deletion, edge deletion, and edge contraction, which will give me the required K5 or K33, and
sure.
the user can easily verify it in polynomial time whether
Right.
that sequence of edge deletion, vertex deletion, and edge contraction will give me the required K5 or K33 subgraph.
Sure. Yeah. You can either do it that way, or you can also use the other way of looking at minors that we discussed, where you have these sets. You delete some vertices v0, and then you give them the sets v1, v2, v3, v4, v5. And supposing you're looking at k5, right? So you will have edges between all of them, stuff like that. Okay, so you can either give a sequence of vertex edge deletions and contractions, or you can give them this partition of the vertex set. Does that make sense? Okay, and for subdivisions it is even clearer. You just give them the subgraph and tell them that, hey, this is a subdivision of k5 or k33 in my graph G, and the person can check this in polynomial time quite easily, right? Given a graph, whether it is a subdivision of k5 or k33, this is easy to check. Okay, that you can think about. So the answer to this is yes, due to either due to Kuratowski or due to Wagner's theorem. Okay, and it turns out that the problem is also polynomial time solvable. This requires an algorithm, right? And since we have 5 minutes, I'll probably say a few words about this. So there are multiple algorithms for planarity. I think it's also linear time solvable, but I'm not going to discuss that. My interest is mostly just convincing you that it is polynomial time solvable, right? I think you get something like n square or n cube. But since the number of edges is linear in the number of vertices, yeah, I think it's n square. Anyways, doesn't matter. Order n square. So how does this algorithm work? So the one that I want to discuss is using the theory of bridges. Okay. So what you do is you take your input graph G, and I think we assume that G is non-separable. Let's say G is a non-separable graph. If you like, you can take a 3-connected graph. It doesn't matter. Okay. And now what you do is you find a cycle in this graph that is, you want to get smaller graphs. So there's going to be a recursive algorithm. We want to break this graph into smaller graphs using cycles and their bridges. Okay. So what we'll do is we'll find a cycle that has at least 2 bridges. So what are we calling them? These are separating cycles. So find a separating cycle, and you have to prove that it exists, but I'm not going to discuss that. Find a separating cycle if one exists. Okay. So let's say you find a separating cycle C. Okay. Because it is a separating cycle, it will have a bunch of bridges, at least 2. Okay. So let B1, B2 up to Bk denote the bridges of C. Okay. So the idea is to recursively call the algorithm for the smaller graphs that are formed by taking a cycle, taking this cycle, and taking any one bridge. Okay. So we recursively call the algorithm on the cycle C union Bi for all I in 1 up to k. If any of these graphs is non-planar, then the whole graph G has to be non-planar, because these are subgraphs of the given graph. If any of them
So basically, we are
Yeah.
finding a separating cycle in G,
Uh-huh.
and we are looking at the bridges of the separating cycle,
Right.
and then we are branching, and then we are recursively invoking the algorithm on each of those individual respective bridges, union the cycle.
Exactly.
Okay.
Exactly. Okay. So if any of these returns non-planar, then you return non-planar and you terminate the algorithm, right? Okay. So now suppose that,
But
yeah.
I have a question. So what
Hmm.
happens if the graph has no non-separating cycle?
Right. So that is your base case. Good. Good point. So that any recursive algorithm has to stop at some point, right? So that's called the terminating condition or the base case, because recursion is just induction, right? And that you just so you basically characterize graphs that do not have separating cycles. So terminate otherwise. Um, and in this case, the graph will always be planar. So I'll tell you what the answer is. So the only non-separable graphs that do not have separating cycles are the cycles, and you add one path to the cycle, one year if you like. You can show that these are the only graphs that are non-separable and do not have any separating cycle. And these graphs are planar.
Okay, okay, got it.
Okay?
So basically, if the graph G doesn't have any separating cycle, then we can
Hmm.
immediately say that G is planar.
Exactly. Exactly.
Otherwise, we will take the
Yeah.
separating cycle and we will consider the bridges with respect to the cycle,
Exactly.
and then we will recurse.
Exactly.
Okay.
Okay?
Okay, fine.
Okay. So now supposing that all of these return planar. Now suppose that C union Bi is planar for all of the bridges 1 up to k. Okay, so now what you have to decide is which bridges to draw inside and which bridges to draw outside. Can you always do that or can you not do that? So the main decision you have to make is decide which bridges are drawn in the interior of C and which ones in the
So, sir,
exterior of
I
C.
have a solution to this problem. So basically, we have collection of some k bridges B1 to
Mm.
Bk, and
Mm.
each of those bridges is planar. We know, because if some is non-planar, then G is non-planar.
Yeah.
So if every bridge is planar, we know every bridge will either be an external bridge or an internal bridge.
Mm.
So now, if so, basically what I'm doing, so some bridges will be internal and some bridges will be external.
Yeah.
So basically, our goal is to determine whether we can partition this set of k bridges
Mm.
into two sets,
Mm.
such that in the first set,
Mm.
every two bridges they avoid each other pairwise,
Exactly.
and
Right.
also in the second set,
Yeah.
every two bridges pairwise avoid each other. Then only
Right.
we can just say that, yeah.
Exactly. Okay, that is exactly what you have to do. So, supposing I have k, let me consider the case of, let's say I consider k equal to 3, just for the sake of example, right? So I look at the first bridge B1, and let's say I draw it inside. Okay. Now, if B2 overlaps with this bridge, then B2 definitely has to be drawn outside because we know that inner bridges avoid each other. So overlapping bridges both cannot be drawn inside. So if B1 and B2 overlap, then B2 has to be drawn outside. Okay. Now if B3 overlaps with B1, then it has to be drawn outside. But if it also overlaps with B2, then it has to be drawn inside. Okay. So what you are seeing here is some kind of bipartition of the bridges. You
Yes,
are
sir.
trying
Because
to
basically,
partition the
what we can
bridges.
do, we can
Exactly.
consider a vertex with respect to the each bridge,
Yeah.
and
So
two
anyway, so
vertices will be
that's
adjacent if and only if they
yeah,
overlap.
exactly.
Basically, yeah.
So we construct what is called the bridge overlap graph. So there is a thing called the bridge overlap graph H. So each bridge is a vertex of H, and two bridges are adjacent in the graph H. So remember, maybe I should say two vertices. Two vertices in H are adjacent if and only if the corresponding bridges overlap. Whenever two bridges overlap, we will put an edge between them. Okay, between the corresponding vertices. All right. And now the main point is that you have to check whether this graph is bipartite. Check whether H is bipartite.
That can be done in polynomial time.
Exactly, right? And if yes, if it is bipartite, then G is planar, because for all the bridges that are on left side in the bipartite graph, you put them inside, and all the bridges that are on the right side, you put them outside. Okay, so the only case when you cannot say the graph is planar is if this graph is an odd cycle. Otherwise, H is non-bipartite, and this implies that the graph G is actually non-planar. If you find three bridges that are all overlapping with each other, for example, which means a three cycle in the graph H, then you will put one bridge inside, you will put the other bridge outside, and now the third bridge, it can neither go inside nor go outside because it is overlapping with both of them. Okay, so that is the entire algorithm. Maybe I'll just say end of algorithm because we did not prove things like correctness
So
and all
basically,
rigorously.
sir, the only way when every bridge is planar but G is non-planar is that H is non-bipartite.
Yes, so in this algorithm, it is only when you find that H is non-bipartite, some bridge overlap graph is non-bipartite, only then will you conclude that the graph G is non-planar. So non-planarity, in some sense, reduces to checking bipartiteness. Okay. Anyways, I think I've gone quite a bit above the time, but all of this stuff was not meant to be on the course syllabus, right? So this algorithm and all is just extra information.
Yes,
It's
sir.
not part
Actually,
of the
the
syllabus.
idea is really nice.
Yes, that's why I thought we have some time, so I'll take the time to explain it. But if you're interested in going into more details, check out my other course around lecture 15 in advanced graph algorithms. And I spell out many more details there. We actually spent a lot of time on this algorithm. Okay, so that's it for planarity. And on Monday, we start graph colorings. Again, we will start from coloring planar graphs, and eventually we'll move on to general graphs. Okay. So feel free to leave. I'm still here for another 5-10 minutes in case any questions.
Okay, sir. Then I'm leaving. Bye.
Okay, see you.
Bye. Bye.
Yeah, Krishnan, your mic is again creating a lot of disturbance. Can you actually leave the call and join the call again? I'll stop recording now, but I'm still here.